Reaction wheels are critical components in spacecraft that are used for attitude control or orientation adjustments. They are part of the Attitude Control System, or ACS, which allows a spacecraft to point in a desired axis without using fuel or external forces like thrusters. Reaction wheels achieve this by exploiting the principles of angular momentum, providing precise control over the orientation of the spacecraft in space. The operation of reaction wheels is based on the principle of conservation of angular momentum, a fundamental concept in physics. Angular momentum is a property of any rotating object and is conserved in an isolated system, meaning that the total angular momentum remains constant unless acted upon by an external force. A reaction wheel system typically consists of one or more flywheels. They are rotating discs mounted on the spacecraft, each driven by an electric motor. The spacecraft can change its orientation by varying the speed of these flywheels. Here's how it works in detail. When the spacecraft needs to rotate around a particular axis, the reaction wheel to that axis is accelerated or decelerated in the opposite axis. The change in the wheel's speed creates an equal and opposite reaction on the spacecraft, causing it to rotate. For example, if the reaction wheel spins faster in a clockwise direction, the spacecraft will begin to rotate counterclockwise. The direction and speed of the spacecraft's rotation depends on the direction and magnitude of the change in the reaction wheel's speed. Typically, a spacecraft has at least 3 reaction wheels, each oriented along one of the 3 principal axes of pitch, yaw, and roll. This setup allows the spacecraft to control its orientation in all 3 dimensions. In some cases, a 4th wheel known as a skewed wheel is added to provide redundancy. This means that if one wheel fails, the spacecraft can still maintain control over its orientation. The reaction wheels work by changing their angular velocity, but the total angular momentum of wheels and spacecraft combined remains 0 in the absence of external forces. This balance allows the spacecraft to maintain or change its orientation while conserving energy. The spacecraft's onboard computer uses sensors like gyroscopes and star trackers to determine its current orientation and calculate the necessary changes to achieve the desired attitude. It then adjusts the speeds of the reaction wheels accordingly to rotate the spacecraft to the correct orientation. Reaction wheels offer extremely fine control over a spacecraft's orientation. This precision is crucial for missions requiring exact pointing, such as Earth observation, scientific experiments, communication with Earth, or aligning precise instruments like telescopes. Unlike thrusters, which rely on expelling mass or fuel to produce thrust, reaction wheels operate electrically and do not consume fuel. This allows the spacecraft to maintain its orientation over long periods without depleting its fuel reserves, extending the mission's life. Reaction wheels operate silently and without producing vibrations, which is essential for sensitive instruments on board that might be disturbed by mechanical noise. For example, telescopes or cameras on spacecraft need to be very stable to capture clear images. Reaction wheels are generally reliable and can function for many years without failure. However, they are not without risks. The wheels can experience friction and wear over time, which might lead to failure. This is why many spacecraft carry multiple wheels, and some use alternative systems like control moment gyroscopes or magnet motors for backup. In many spacecraft, reaction wheels are part of a larger attitude control system that includes other components like control moment gyroscopes, thrusters, and magnetorquers. This redundancy ensures that the spacecraft can still maintain or adjust its orientation, even if a reaction wheel fails. Reaction wheels have been used in a wide range of space missions, from small satellites to large space telescopes and interplanetary probes. Some notable examples include the Hubble Space Telescope, which uses reaction wheels to maintain its precise orientation needed to capture images of distant celestial objects. Earth observation satellites, which rely on reaction wheels to maintain a stable platform for capturing high-resolution images of the Earth's surface, and deep space probes like the Voyager missions, which use reaction wheels to adjust their orientation for communication with Earth and to align scientific instruments. Reaction wheels are vital for the effective operation of spacecraft, providing precise and efficient control over their orientation. By leveraging the principles of angular momentum, these systems allow spacecraft to perform complex maneuvers, maintain stability, and execute missions over long periods without depleting their limited fuel resources. As space exploration continues to advance, reaction wheels will remain a fundamental component in the design and operation of spacecraft, ensuring the success of future missions.